Hello, this is FlippedHarber for Algebra 2. In this video we'll be covering section 4.3, using matrices to transform geometric figures. Now, what we're going to be doing is starting by creating a matrix by storing points in that matrix. The thing to remember is that this matrix will have two rows. The top row will be all of the x-coordinates for the points for our figure. So if we have a triangle that we're trying to put into a matrix, we're going to have three x-coordinates making up the top row. The y-coordinates go in the bottom row. Each column represents a point. So triangles have three columns, quadrilaterals have four, so on and so forth. Each column is a point. The x value goes in the top, the y value goes in the bottom. Now, here we see the matrix for the triangle ABC, where A is the point -2, -1, B is the point 0, 3, and C is the point 1, -2. So this matrix is just a way to store this data that is the y-coordinates and the x-coordinates for the 3 points. Now we're going to be multiplying this matrix by numbers. We're going to be multiplying this matrix by other matrices. We might even just be adding numbers to this matrix in order to make some transformations happen. So let's take a look at how these transformations happen. First of all, a translation matrix in geometry moves the objects left, right, or up or down. A translation matrix has the x translation in the top row. That is, if we want to move the objects left or right, we put however far we want it to move left or right in the top row of the translation matrix. However far we want to move it up or down, that's a change in the y-coordinate, goes in the bottom row. You are going to have to make the translation matrix for your homework, and you have to make sure that you make it the same size as the coordinate matrix. So if we have a coordinate matrix for a triangle, it's a 2 by 3 matrix. Your translation matrix is also going to be a 2 by 3 matrix. If we're talking about translating a square, the coordinate matrix is 2 by 4, so you have to make the translation matrix also being 2 by 4. Now, whenever we use a translation matrix, that is to move it left or right, up or down, we just simply add it to the coordinate matrix. So, here's an example of translating the triangle ABC, right 2 spaces, and down 3 spaces. So we fill that coordinate matrix with our points, -2, -1, 0, 3, and 1, -2. And then the translation matrix has 2's all the way across the top because that's going to move it right 2 spaces. The bottom row is the same number all the way across. It's -3 because that's going to move the triangle down 3 spaces. So your translation matrix has the same size as your coordinate matrix, in this case 2 by 3, and the top row is filled with the same number. The bottom row is filled with the same number. And here we see our answer coordinate matrix, our image, it's often referred to as, and it's moved the point -2, -1 to the point 0, -4. And we see a new spot for point A. It's called A primed, or it's referred to as the image of A. And B has a new spot, 2, 0, and C has a new spot, 3, -5. So this is how we handle translations with matrices. Now, a dilation is where we make an object bigger or smaller. Now, it doesn't change the shape of the matrix. It just, the shape of the object. It just makes the object bigger. If it's a triangle, it stays a triangle. If it's a right triangle, it's still a right triangle. It's just going to be bigger or smaller. In order to do this with our matrices, all we need to do is some scalar multiplication. If we multiply by a number bigger than 1, like 2 or 3 or 4, the figure gets bigger. If the scalar is smaller than 1, a fraction or a decimal, then the figure gets smaller. So here we want to reduce triangle ABC with the given coordinates, so this is a different triangle ABC than we've seen, by a factor of 1/2. So they're telling us what to multiply by in order to make this happen. They want us to find the coordinates of the vertices of the image, that's the new triangle, and they want us to graph it. So we're going to multiply each coordinate by 1/2. And the way we're going to do that is by multiplying each entry in the matrix by 1/2. So this is a good use for scalar multiplication. So here we see that scalar multiplication, the 1/2 out in front of the matrix, and we multiply all 6 numbers inside the matrix by that 1/2. We see our new x coordinates, we see our new y coordinates, and now all that's left to do is list the new points. A primed, or the image of A is referred to as is -2, 0. The image of B is 1, 2. And C primed, the image of C, is 2, -1. And here we see a graph with our original triangle ABC and the new smaller image. Okay, so let's talk about reflections. Whenever we want to reflect over the x-axis, we can accomplish that by multiplying by this 2 by 2 matrix. Now this top row, 1, 0, is going to leave the x coordinates alone. The bottom row, 0, -1, what it will end up doing is changing the sign on all of our y coordinates. And that's what happens when we reflect over the x-axis. We leave our x coordinates alone, and we change the sign on all of our y coordinates. So this matrix does this to our matrices that we're going to create for shapes. Reflecting over the y-axis, we use a very similar matrix, -1, 0, 0, -1. That top row is going to change all of our x coordinates, going to change the sign on them. That bottom row is going to leave all of our y coordinates the same. Now, something very special to remember, regardless of what size our coordinate matrix is, regardless of what shape we're working with, these reflection matrices always go in front for the multiplication. So you always start with this matrix followed by your coordinate matrix. So let's take a look at one. We want to reflect the triangle JKL with the coordinates shown across the y-axis. Now, in your homework, you can look up what matrix to use in order to do that. In a test situation, I'll help you out. I'll tell you what matrix will reflect across the y-axis. You don't need to memorize this. I really don't think that's the point here. But you're going to need to know what the heck to do with this matrix. So I'll give you the matrix on a test. This is what you need to use to reflect over the y-axis, but you're going to need to know what to do with it. So this is what you do with it. You put that reflection matrix in front, and it multiplies our coordinate matrix. Now you go through the process and you can see that that top row, all of our x coordinates have changed sign. Instead of 3, 4, 1, they're now -3, -4, -1. But the y coordinates are unchanged. They're still 4, 2, and -2. So that's why this is a reflection over the y-axis, because those x coordinates changed signs, but the y coordinates did not change. Now, what we're going to do is take a look at a graph for this. We can see the original triangle, JKL, in the blue, and the image triangle, J primed, K primed, L primed, is in red, and you can see that they've all been reflected over the y-axis. Now again, you're not going to need to memorize what your reflection matrices are. You can ask for those, I'll give them to you, that's no problem, but you need to know what to do with them. Okay, so here's another reflection. I'm not even going to bother to talk about what the reflection is. It's a reflection matrix. We're going to multiply by this reflection matrix in order to see what happens here. So our coordinate matrix has the points -2, -1, 0, 3, and 1, -2. When we multiply, that top row is going to leave the x coordinates alone. So they're going to stay -2, 0, and 1. That bottom row, the 0, -1, is going to change the sign on all of our y coordinates. Oops. So what this is going to be is a reflection over the x-axis. Okay, so moving on. A rotation is also multiplying by a matrix in order to get the rotation done. You're just going to be given the rotation matrix. You really don't need to worry about how far and in which direction it's rotating. And again, this rotation matrix, which is going to be a 2 by 2, comes first in the multiplication. So here we want to use a matrix to take the polynomial JKLM. They give us the coordinates, and they give us those coordinates so that we can make the coordinate matrix. And they want us to graph and describe the image. So they're giving us the rotation matrix. We really don't need to worry about really what it does. We just need to apply the multiplication. So again, that 2 by 2 matrix goes in front. And you can see that all of our, well, almost all of our x coordinates have changed. Almost all of our y coordinates have changed. Those zeros in the first column have actually traded spots, basically, is what they've done. And let's take a look at a graph for the image and the original shape. So the original shape is in the blue, and we can see that it's been rotated counterclockwise. The red image has been spun about the origin, and how far has it been spun really doesn't matter. But this trapezoid, JKLM, has been rotated counterclockwise to create the image J primed, K primed, L primed, and M primed. Okay, so let's do this again. We have a polygon JKLM, and we want to use this rotation matrix. They're just going to give you the rotation matrix. You just need to know to put it in front and multiply by it. So that's exactly what we're going to do here. We're going to put that rotation matrix in front. We're going to use our matrix multiplication in order to make this happen. And you can see that our y coordinates have become our x coordinates. Our x coordinates have changed sign and become our y coordinates. So let's take a look at this rotation, and we can see that our blue shape has now been rotated clockwise. Okay, so that's it. It's time for you to try some of these on your own. I'll see you in class, and I will see you online.